All right, guys, today we're going to take a look at Unit 5, kinetics. This is our first topic on reaction rates. So we will be explaining the relationship between the rate of a chemical reaction and experimental parameters. So kinetics is an interesting area of chemistry, and it's defined as the rate or speed at which an amount of reactant is converted into products per unit of time. So essentially, kinetics studies the speed of reactions. Now, just to clarify, reactions in chemistry are sometimes expected to be fast, to almost be instant, but reactions in chemistry can take seconds, minutes, hours, days, years. Nuclear reactions, the decay of radioactive material, can take millions of years even sometimes. So it does vary. So our unit of time can change depending on the reaction. So some examples of just general rates would be things like my car has a rate of 60 miles per hour. So we would show that as 60 miles over 1 hour. So per means over 1. Or I eat 2 snacks a day, so 2 snacks per day. If we're looking at a reaction, we could say 0.0030 molar HCl is used per second in the reaction. So we can write the amount that is being used over time, and that is the rate of the reaction. So we've got that example there in molarity per second. That is a really common unit of rate in chemistry, is a molarity over time, or moles over time. How much is reacting? Another one might be 0.065 molar NH3 is produced per minute in the reaction. So it can be how much is used up, or it can be how much is being made. And again, it's per a unit time. So all of these are examples of rates, how fast something goes, and they're all set up in an amount over time. So that's when we think about rates, we want to keep that in mind. Now we can take the reaction rate and mole ratios and relate those together. So the rate that one chemical is used or made, produced, can help you determine the rate of the other chemicals in the reaction. We use the balanced reaction to relate the rate of one chemical to the rate of another. Just like we use the balanced reaction to relate the amount of each chemical reactant, we can also relate the rates together. So for example, if our reaction is A plus 2B makes A2B, if chemical A is used at a rate of 1.5 molarity per minute, then the rate that B is used would be twice that amount, because it needs twice as many moles of reactant. So B is going to react at a faster rate because we're using more of it every minute. So the rate of B would be twice as much, which would be 3 molar per minute. We can indicate that A and B are being used by stating it, or we can also show the values as being negative since they are disappearing or being used up. Their amount is decreasing. So if you see a negative rate, you know it's indicating a reactant, or it says the chemical is being used in the reaction. So those are two ways we can indicate that. If we looked at the rate of the product, the rate of A2B is formed, the rate that A2B is formed would be positive because we're making it, we're adding that to the reaction, or creating it in the reaction, and would match the rate for just chemical A by itself, since they are a 1-to-1 ratio. So since chemical A was a rate of 1.5 molarity per minute, the rate that A2B is produced would be 1.5 molarity per minute. So that's how we can relate our chemicals and their rates to our balanced reaction and their mole ratios. All right, let's take a look at a couple of examples of finding our rate of a chemical. So if the rate of hydrogen reacting is negative 3 times 10 to the negative 3 molarity per second. So the negative indicates that hydrogen is disappearing. Part A says, what is the rate of the nitrogen reacting? So we want to know the rate of the reaction for nitrogen. So we can take our hydrogen, that's given, and essentially what we're going to do here is a mole ratio. We're changing chemicals. So we're going to set up a mole ratio changing from hydrogen to nitrogen. We use our coefficients from the balanced reaction, And that means that we're dividing by 3, so we end up with -1 times 10 to the third, or negative third molarity per second for nitrogen. So essentially nitrogen reacts a third of the speed as hydrogen because we're only using a third of the nitrogen. The negative indicates again that it's disappearing, that it's a reactant, we're using it up, since it doesn't say disappearing or appearing in the question. It's not implied. Part B, we want to do the same thing, but this is the rate of the ammonia forming. So we've got the rate that our hydrogen is reacting. And again, we're going to set that mole ratio. It's a 3:2 ratio for hydrogen to ammonia. And that gives us our answer. Now, the one thing we have to be careful of is the ammonia is forming. So we want to make it positive because it's on the other side of the reaction. So you could add some sort of indication in there that you're multiplying this by a -1 to flip the sign, or you can just put that plus sign there as an indication that it's a product and it's appearing. So that's how we would find the rate of a chemical in a particular reaction given the rate of another chemical. All right, here's another example of this. I want you to go ahead and try it out. Now, this one's just a slightly bit different in that it says if the rate of disappearance of H2O2 is 0.0015 molarity per second. So it's giving you the rate and it's saying it's disappearing instead of writing that it's negative. We wouldn't want to say disappearance and then put a negative on it because those kind of are contradictory. So, or excuse me, they mean the same thing, so it's redundant. So I've set up the equation. Why don't you guys pause, try these two out, and then check your answers. All right. Hopefully you've paused and you've worked out the first one. So rate of disappearance of MnO4-, so the permanganate ion. So we're changing from H2O2 peroxide to permanganate. So it's a 5:2 ratio. So check your ratio. Did you get that right? All right, and then we multiply by 2, divide by 5, and we should get 0.00060 with sig figs permanganate ion. So if H2O2 reacts at 0.0015, permanganate is going to react at 0.00060. All right, and then our last one, let's check that. We've got the rate of disappearance of hydrogen. Again, it's saying disappearing, so we don't have to make it negative. So we're going to change from H2O2 to hydrogen. So it's a 5:6 ratio. Did you get that part right? And then our answer would be 0.0018 molarity per second for hydrogen. We could use this same approach and convert to any of our products. So we could have the rate of appearance of all of our products as well. So these are just a couple of examples of how we can relate the rates together. Now we're going to take a look at what affects the rate of a reaction. So there's a couple of things we can change about a reaction to affect its rate, and this is really what you explored in chemistry last year. This should be a little bit of review. So increasing temperature. We can increase the speed of our particles by increasing temperature. So they're going to they're going to collide more often and react faster with each other. We're going to have more particles that are able to react and form products. We saw this last year in our reaction rates unit towards the end of the year when we looked at the glow stick demo. If you remember that one, we put glow sticks in hot water and cold water, and we saw that the hot water made the glow stick glow more because the reaction was happening faster, so we got more light from it. And in cold water, it slowed down, so we got less light from it. Now, the other thing about increasing your speed of your reaction is your reaction is going to end sooner, right? You're going to have, you're going to run out sooner. So like with a glow stick, that may not be the best thing. It just depends on your goal. All right, another way we can change the rate of reaction, and we're going to be exploring this one the most, is increasing the concentration of our chemicals. So by increasing the amount of a chemical, the chemicals are able to come in contact more often, providing more chances for them to react. So this goes into what's called collision theory, which we're going to get into, and what is required for chemicals to actually have a successful reaction. Well, one of the big things is that they have to touch each other. Well, the more chemicals can come in contact with each other, the more they're able to have successful collisions and react. So increasing that concentration can help with that. So that's generally increasing the molarity or moles of chemical. And then underneath that, it has increasing pressure. So when we deal with gases, instead of increasing the concentration, we think about it in terms of increasing the pressure, right? Adding more particles of gas is going to increase the pressure. This causes the particles to be in a more confined space and collide more often. Our next one is increasing surface area. By changing from a large chunk of a solid chemical to a powdered form, we increase the surface area, allowing more of the solid to react. Again, you increase that contact between the chemicals, so you're able to react more often and collide more often and react faster. We did this one in a lab last year on, I believe, using magnesium and hydrochloric acid. It might have been a demo too. Not sure, can't remember that one, but using solid magnesium versus powdered magnesium, and the powdered is going to have a much faster reaction rate. And the last one is adding a catalyst. So a catalyst is another chemical that's added to the reaction, and it gives it another path for the reaction to follow and react faster. We are going to explore that part specifically more in depth later in the unit. So we'll get back to catalysts and their function and how they work, but we can also add a catalyst. All right, let's check out this question. So we've got a reaction, C2H4 and hydrogen, making C2H6. So C2H4 is reduced by hydrogen, so this is a redox reaction, in the presence of solid platinum catalyst, as represented by the equation above. So factors that could affect the reaction rate, or the rate of the reaction, include which of the following. So we know it's already got a catalyst, so it's adding a solid platinum catalyst, but other ways that we could change the rate of the reaction. So we want to pick any of them that would apply. So it says changes in the partial pressure of hydrogen. Well, hydrogen is a gas. If we increase that pressure on hydrogen, we can make it react faster. If we decrease hydrogen, it can make it react slower. So that's definitely an option. Changes in the partial pressure. I'm just highlighting them. Changes in the particle size of the platinum catalyst. Again, particle size is a way we can affect the rate of a reaction. So if we have more particles, it can help the reaction along. And the third one, changes in temperature. If we increase or decrease the temperature, that will change the speed of the reaction. So all of these would be factors that could affect the speed of the reaction, all three of them. All right, looking at this one, we got the same reaction there. Which of the following is most likely to increase the rate of the reaction represented above? So we want to increase the rate. We want to make it go faster. So let's see, decreasing the temperature of the reaction. Well, if we decrease it, the particles slow down. They're not going to collide as often. So it would not be a good option to decrease our speed of our particles. Increasing the volume of the reaction vessel using a piston. When they say a piston, it's basically like a plunger. So you'd have your container and then you'd have a part that can move up and down. This part that you can pull up and pull down, kind of like a syringe has that plunger on the end. So increasing the volume would be pulling this out. Well, if we do that, the particles are going to be more spread out. So than they would be if it was all pushed down. Let me draw something like that. So if they were pushed down, they'd be closer and they'd collide more often, so they would react faster. So increasing that volume doesn't really help us react faster. Removing some hydrogen from the reaction. By removing some hydrogen, we're decreasing its amount or its concentration. So there's less likely to collide. We're going to have less reaction. So it can't be that one. So it must be the last one. Increasing the pressure of the reaction vessel using a piston. So to increase the pressure, we would have to decrease the volume. So it would be going from the one on the right to the one on the left, opposite. pushing it down. So it pushes the particles together, we increase their number of collisions, and they would increase their rate of reaction. So with all of these types of changes you can make on a reaction, go back in your brain as you think about them to the collision. Is there going to be more or less? And that can help you decide if it's going to speed up or slow down your reaction. It's a really fundamental way of thinking of these. All right, let me know what questions you have in class, and thanks, guys.